welcome back. Now we're going to start cracking into our next section, which is that of limits, constant, and continuity. So we've spent a lot of time looking at sequences and understanding the convergence of sequences and all sorts of things relating to that. But now we're going to move on to sort of the main object of study for real analysis, which is functions. So now we're talking about functions on the real line, so all the things that we know and love from earlier calculus courses you may have done. And we're going to understand limits and continuity for the time being, and we're going to develop rigorous, careful definitions of these things that will help us put what we're going to do after that with differentiation and all that kind of stuff on a firm footing. So what we're going to start with is, for a bit of an introduction, is just to think back about what our notions of limits and continuity are that we're bringing into this course. So probably your conception of a continuous function, so let's see if we can sketch one. And it's a pretty good definition for what we've used it for in the past, is probably that a function is continuous if you can put your pen down on the paper and you can draw it with no gaps. Okay, so here is our continuous function equals continuous. Okay, you can put your pen on the paper, you can draw the function without picking a pen up, therefore it must be continuous. And maybe for limits, if we were to take a point on our function, let's just plop one on there. This can be f of c and c, so c down here, and function value f of c. If we want to say the limit, our understanding of what limits are, limit as x tends to c of f of x equals c if. Now, the way we've sort of understood this is that as we get close to it, well, this is the way that I initially understood limits, as I get close to this point here, okay, as x gets close to c, then my function value must get close to f of c. And again, that's a pretty good hand-wavy explanation of what a limit is, but we can see that it doesn't quite satisfy enough rigor for this course. It's hard to quantify exactly what that means. But nevertheless, it's a good intuition. So if as x gets near c, f of x gets near f of c. Now you probably also remember from when you've studied this before that what actually happens at c is completely irrelevant. So I probably shouldn't have called that f of c. It gets near some number. I'll just leave it as f of c for now, we'll fix it later. But actually, if there was a hole in my function here, if that wasn't actually there, let's put our function back, I didn't mean to delete the whole thing. If there was a big gap here, then the limit would still apply. We remember that. So we might have had a function where for some reason the function value is defined to be up here, and you probably remember that the limit as I go to c is still that same value where f of c should have been. And yeah, that was kind of how it worked. Okay, and it was for the function to be continuous, we would have required that limit was f of c. Okay, if the function was continuous, then the function would have had to be this value here that everything was tending to. Okay, so what we want to do is we want to build on the work that we've done with sequences because we understand the limits of these pretty well, and we would like to see if we can piggyback on some of that work and turn it into a statement about the limit of functions. So here's sort of an approach that we might consider. If I take a sequence, so let's just sketch a fresh picture, that one's getting a bit grubby. Here's a function, let's just make it a little bit less complicated before. If I take a sequence of values here, so I'm taking a sequence which is converging, hopefully that looks kind of like converging, to some value c. Then if I do that, then I get a corresponding sequence of function values. Okay, so this could be my x1, x2, x3, etc. Then if I look at the function of these values, then I'll get f of x1. Let's make them red, shall we? We'll get I've drawn this in the worst possible place on my picture. Let's make this curve less flat so that I can actually see that a little bit better. If I draw my function values now, f of x1 will now be about here. And you can see as I get towards c, it looks like these red values are converging towards a value as well. So this will be f of x1, f of x2, etc. So you can see that we've got two sequences here automatically. I've got a sequence that converges to C, and then I can just take the function value of all those sequence terms, and that gets me another sequence which is hopefully going to converge to some number B, which is what I want to be the limit. So maybe our first definition, or our first attempt at a definition, would be let xn tend to some c. Then the limit as x tends to c of f of x is equal to the limit of the sequence of function of our sequence values. That seems actually pretty reasonable, right? We've got a sequence that converges to C. Maybe we could express this limit in terms of the limit of the function values. Again, this doesn't require us to actually evaluate our function at C. Right? There's nowhere in this definition is f of c actually necessarily appearing. So that we haven't violated that kind of guideline that we started with. And that all looks rather nice. So maybe this is a good choice for our limit definition if we tidy it up a wee bit. But actually, turns out it's not, and we can fabricate some horrible examples that actually make this definition fall down. So I'll just make some space. Here's a function that I'm going to define. It's a very strange function. It was proposed by Peter Dirichlet, and it is the following. G of x is equal to 1 if x is rational, and it's equal to 0 if x is irrational. Okay, what does that look like? Well, let's see if we can sketch it. Now, remember the rational numbers, we proved this earlier on, they're actually densely packed in the real line, and so too are the irrational numbers. So problem is we have function values. F of x has all these gaps in it because we know that the real numbers have gaps, so the rational numbers have gaps, and so do the irrationals. And so if we were to attempt to sketch this thing, which is not actually possible, it would look something like this. Okay, densely packed sets of points between 1 and some of them are 1, some of them are 0, and that is the horrible thing that we have. Okay, so what I'm going to do is I'm going to try and see where my limit definition is going to break down. So I'm going to choose a sequence that converges, let's say, to a half. Okay, so I'm going to have a sequence of x values that converges to a half, and I'll call this sequence x1. All right, and I'll just make it, let's call this xn. Converges to a half, and I'll also make it that xn is rational. But I could make another sequence, and I'll call this one Sn, that converges to a half. But this time I'll make it a sequence of irrational numbers. So here we go. We still remember these are the x values. Here's my Sns. This one over here was my Xns. But the sequence of f of Sn is actually up here, whereas my sequence f of xn is down there. So xn tends to a half. I've specified that Sn is not in Q. The problem we have here is f of xn, that sequence, quite clearly converges to 0 because my function is defined, I should have called it f, not g. Let's call it f now. My function is defined to equal 0 whenever we have I've done this back to front. Let's just say that's not rational and this one is rational. Sorry about that. So just double check. My first sequence is 0, so it's going to be the irrationals. So f of xn converges to 0. But if I take my function value of all of my Sn terms, they're all equal to 1. So that sequence converges to 1. So our definition should have told us that this limit doesn't exist. And at the moment it does. Our first attempt is to take a sequence and then define the limit to be the limit of that sequence. What we're sort of accidentally assuming here is that our function has nice properties, that it's we're kind of imposing continuity on it by accident in the way we've conceptualized it. We haven't allowed it to do these crazy things like this discontinuous monster at the bottom does. So we need to be a little bit more careful about our definition of a limit, and in fact the correction that we're going to make is we're going to make sure that every sequence that converges to C, with a couple of technical restrictions, has the same limit of function values. And if that's the case, then that will actually give us the definition of limit that we want. Okay, so before we do that, we're just going to have a preliminary definition that we're going to work with, and it's the notion of a limit point or an accumulation point. Same word, so different words, same concept. So if A is a set of real numbers, then a real number is a limit point of A if a sequence AN tends to X, so X is the number we're talking about, for some sequence in A where none of the terms are actually equal to X for all N in the natural numbers. Okay, that sounds a lot worse than it is. Let's just look at an open interval of the real line, just to fix this in it. So let's just take a point here. First question, is this point a limit point? Yes, it is, because we can construct a sequence that converges to it. Okay, so remember that none of the terms of the sequence are allowed to be equal to our value x. That's fine, and all of the sequence terms have to be in A. That's fine too. And the limit of the sequence has to equal x. That's fine too. It's not very hard to fabricate an example that comes up with this idea. Okay, so that x as drawn here is definitely an accumulation point, so we'll give it a tick. What about one of the endpoints? Okay, it's not actually in A. It's an open interval. This point here is not actually within the interval, but it is a limit point of A because, again, we can build a sequence of values that converges to this point where all of these things are in A. None of these things are equal to x themselves, but their limit is equal to x. Okay, so the limit points for our open interval here are all of the points within it plus the endpoints. What if I took a point off the end of the interval? So let's just, that one gets a tick as well. Does this one get a tick? No, it does not, because there's no way I can build a sequence in A that converges to this value of x over here. So that one is not an accumulation point or a limit point. Okay, so this is the idea, and essentially the idea behind these limit points, these are the values that we're allowed to take the limits at. Okay, so you know how we always write the limit as x tends to a of something. Okay, this thing here, we're going to require that it is a limit or an accumulation point. So let's write limit point because it's easier. Okay, so the limit points are the values that we can take the limits as x goes to. Right, so that's our tidy definition of what a limit point is. Just a little technicality, and we're going to enforce that when we define our limit, that this value a has got to be a limit point. Okay, so that just clarifies that one. So here we have our definition of a functional limit, and we're calling it the sequential criterion for function limits because, as it turns out, we're going to state a theorem that is equivalent to this but looks quite different. And in fact, either one of these could be taken as the definition, and we're going to prove that the two are equivalent. So we're going to start with the sequence version as our definition because that's how we started our argument, but we could equally well go the other way. Right, so here's our definition of a limit. So f is a function, a is an accumulation point of the domain of the function. Okay, so we're saying that we can't take the limit of any value that's not a limit point of the domain. Again, technicality, most of the time we won't really have to deal with this. For most problems we encounter, this would be automatic, but we do need to just be aware of it, that it is a thing. So we've got a function. First thing you should always be thinking of is, what is the domain of this function? Is my limit value contained within the domain or at the end of it? And b is a number. Then we're going to define the actual limit, which is this one here. Okay, two different notations. Sometimes the second one is more convenient than the first one. If the sequence f of an converges to b, so b is our limit, whenever, okay, that means for every possible sequence an that's in the domain, excluding the limit point, that converges to a. Okay, so the sequence has to be in the domain of the function, otherwise we couldn't calculate these function values. We also make sure that the sequence values are not including the limit point itself. It's not very hard to make sure that that holds. And then so long as every possible sequence you can choose in the domain of this sort has f of an converges to b, then the limit of the function is defined to be b. And now we have the alternative characterization, which is the possibly, if there's a chance you've seen a formal definition of a limit before, then this may be the one you've seen. So like I just said, this could actually be taken as our definition, and then we could show that the sequence version is equivalent to it. So either way around doesn't matter, but we're going to state it as a theorem. So we're going to have the f be a function, a an accumulation point of the domain, and b a number. And b a number. Let's just put it in b be a number. Okay, so same setup as the previous one, otherwise we couldn't show that the same thing. Then this time we've got this limit, if and only if. Okay, so remember, if and only if is going to establish the logical equivalence of two different statements. And here is our what we call the Epsilon-delta version. So for every epsilon greater than 0, there exists a delta greater than 0. Okay, so this is familiar template pattern to our sequence convergence, isn't it, where we had epsilons and n's. So we've got two quantifiers, epsilon and delta, such that the absolute value of f of x minus b is less than epsilon. Okay, that's like our sequence epsilon as well. Whenever we have x in the domain and 0 is less than absolute value of x minus a is less than delta. Okay, now just like with sequences, this is easiest to understand if we put it in a picture. So let's draw ourselves a function. What color should we go for? Let's go for a green function. Here it is. So we've got our points A and B. And just like with the function, the sequences, remember we said the whole idea was no matter how small you make epsilon, we could find a corresponding n. So for our functions, it's a bit different, but the same also. Again, we're going to specify a level of closeness to b that we want, and we're going to call that epsilon. So we'll draw this band over here. Now with our sequences, we then went off as far as we could to the right, finding terms of the sequence that fit within this band. That doesn't work here because obviously we don't have a sequence at this point. But what we want is to make sure that we can find a delta so that this inequality here, let's just circle that one, enforces us to be within this band. So the way to understand this on the picture is actually the question is saying, once we've chosen this epsilon, is it possible to find a delta so that if I go within delta of a, so this will be a minus delta, this will be a plus delta. If I get that close to a, then my function, my green function, the green part of the function there is going to be entirely contained within that box. So remember, epsilon has been fixed as like a challenge. The challenge is, can you make my function within 0.001 of b? Answer is, can I find a delta so that if I get close enough to a, my function is entirely contained within that box. Note that it excludes a itself, so if this function was doing something weird, actually at a, it wouldn't matter because we don't see that. That's why it's got this less than there, so x is not actually allowed to be equal to a. But what we have is this thing here, if we can find a small enough delta, so let's just draw an example of what a too big delta would look like. If delta was this big, if we had a plus delta over here and a minus delta over here, then clearly there'd be some parts of the curve that were outside of our red band. So we'd had to bring delta smaller to get it closer to a, and hopefully, if the limit exists, there will be a value of delta which is small enough so that the entirety of the green curve is contained within our box. Okay, which is equivalent to saying that f of x minus b is less than epsilon, or Yeah, the absolute value of f of x minus b is less than epsilon. So it would pay just to rehearse this a wee bit. We'll do some examples of some simple problems just to understand how this works. But before we do that, we better actually prove that this is equivalent to the sequence definition. Otherwise, it's entirely meaningless. All right, so let's prove this thing. Now, because it's an if and only if theorem, we have to prove both directions. So we're going to start by assuming that the epsilon-delta property is true. And we're going to show that the limit defined in terms of sequences also holds. Right. This is going to get a little bit tangly. So the first thing we have to do is figure out what it is we actually have to do. Okay, because if we can't figure that out, then we can't make any progress at all. So we have to show that the limit works. Okay, so we need to show that we have a function and the limit, we have to show that any sequence converging to our point A is also going to have the function values converging to that point. That's what we've been asked to show. So there's a lot of setup we need to do here just to make sure everything is defined. So if we just go back for a second, we were told that we have a function, we were told we have an accumulation point, and we were told that we have a number b. Okay, so that's what we've got set up for us already. So we've got our accumulation point a, we've got our function, and we've got b, which is the number that we hope to be the limit. So to show this, we need to take a sequence in the domain of our function minus the limit point that converges to a, and we need to show that its function values converge to b. So it will start with something like this. Let an be a sequence in the domain of our function minus a point A with an converging to A. Right, this is going to be our sequence that we've got that converges to A. We want to show that our sequence f of an converges to B automatically. That is, we are asking to show that a certain sequence converges to a certain number. Right, so just make sure you're happy with that. So we've got a sequence in our domain. This is the type of sequence we have that converges to A. And we need to show that its limit of its function values converges to B. I.e., that's gonna, we're back to doing a standard sequence convergence problem. So let epsilon be greater than 0. We seek n such that if n is greater than or equal to n, it follows that the absolute value of f of an minus b is less than epsilon. Okay, so that was a bit tricky, but just because we had so much stuff floating around in this problem that it's a bit hard to get your head around what it all is. But this is essentially what we've got. We've got ourselves a sequence that was specified, so maybe I'll highlight the things in yellow that were specified as part of the problem. Okay, we've got ourselves a function, we've got ourselves a sequence. Okay, that wasn't specified as part of the problem, but it was specified as we need to show that no matter which one of these we take, we'll always have its function values converges to B. So we've got all that stuff, and now we just actually what we're trying to do is show that a certain sequence converges to a certain value. So this part here is very much just following the template that we've had for most of our convergence proofs so far, which is to let epsilon be greater than 0, looking for an n such that blah is the case. Okay, so if you remember, what we're trying to do is we're trying to spend a little bit of time finding this sequence, finding this value of capital N. Right, and the thing that we're going to have to make use of when finding this n is the fact that we have a convergent sequence an. So no matter what we do, we're going to have to make use of the fact that we have a convergent sequence. So we expect to be using an minus a at some point and making that small. And epsilon delta, what does that mean? Well, that says That says I can make f of x minus b as small as I like by choosing a delta. Okay, and the delta that I get is like a 0 is less than x minus a is less than delta. Okay, so there's some similarities here. I noticed that actually I've got a similar looking term just here and here. I'm trying to make my an minus a small, and I can make that as small as I like because an is a convergent sequence which have been given. So I can control this. Okay, and I also know that if I make an smaller than this delta here, then I'll also automatically be as smaller than epsilon. So here's the step. I want to make f of an minus b to be less than epsilon. Okay, I can choose a delta so that absolute value of x minus an is less than delta implies, sorry, not x minus an, it should be an minus a. Okay, because I'm putting an in here, I can choose a delta so that if this is true, then the thing I want will be true as well. But I know that an is convergent, so can do this as an converges. So, I mean, you may need to take a moment to just convince yourself that this all works. So I've set up, if I go back to my proper proof now, I've set up a sequence that converges to A. I want to show that the function values converge to B. I've started off by setting up my standard convergence template, which is what I'm after. And then I just need to put all the pieces together. So we'll start by putting down what that delta is. So we'll choose delta such that 0 is less than x minus a is less than delta implies absolute value of f of x minus b is less than epsilon. Okay, I'm allowed to do this because I am assuming that as part of, that's one of my assumptions. I'm assuming the epsilon delta property. So I'm choosing this particular delta to make sure that my function value minus b is less than epsilon, and this epsilon is this one that we have fixed at some positive value. Okay, but this delta is basically how small I want to make the difference between a and an. So now I'm going to choose n, such that if n is greater than or equal to n, absolute value of an minus a is less than delta. Okay, so I've chosen delta from the epsilon-delta property, I've chosen n from the convergent sequence property, and now all I have to do is link them together. I also know that an is not equal to a because it's in the domain minus a, so I can also insert 0 in here. Okay, so I've chosen my n. I now just need to demonstrate that f of an minus b is less than epsilon. If I can do that, then we're all good. Okay, so let n be greater than or equal to n. Then absolute value of an minus a is less than delta implies f of an minus b is less than epsilon as required. Okay, so I've just linked up the two convergence ideas together, and it all sort of came together in the end. Now, I'd recommend just taking a little moment over this one to make sure you're happy with how the argument works. You may need to go through it a couple of times, because we're chaining together a couple of different things in one go, and it's just worth seeing imagining which things are fixed, which things we have control over, and how we're linking these things together. Alright, so for the converse, we are going to actually attack this one by contradiction. So what we are trying to do overall is to assume that the limit definition is true and to show the epsilon-delta property follows from that. Turns out this one is easier to attack by contradiction, so we're going to assume the limit one is true and that also the negation of epsilon-delta is true, and then derive a contradiction. So strategy. Contradiction. So we're going to assume that limit definition and the negation of the epsilon-delta property. Alright, so we're going to have to be a little bit careful about that because the epsilon-delta property is quite complicated if we express it in terms of quantifiers. So let's figure out how to do this first. So to negate epsilon-delta, that looks like that. So we're going to take the negation. I'm going to do this in symbols because it's way easier to do if we do it in symbols rather than trying to wordify it all out. So if we were to state our epsilon-delta property in symbols, it says for every epsilon greater than 0, there exists a delta greater than 0, such that for all x, if the 0 is less than x minus a is less than delta, implies f of x minus b, absolute value, is less than epsilon. Okay, so we have three quantifiers and then we have an implication inside, and that's what our overall statement looks like. Now, if you remember back to earlier videos where we looked at logic, we actually know how to negate this kind of thing quite mechanically. We know that we go through and we flip all of the quantifiers, so every for all becomes that there exists, etc. And then the negation of the implication is again going to be the first thing, hypothesis, and the negation of the premise. So that is going to be, we can do this step by step, there exists a delta greater than 0, such that, epsilon, such that for all delta greater than 0, there exists an x such that 0 is less than x minus a is less than delta, and absolute value of f of x minus b is greater than or equal to epsilon. Okay, so that is actually the negation of the epsilon-delta property that we're going to assume to be true. So our strategy is to assume that the sequence version is true and also that our negation is true. Okay, so here's how it's going to work. So if we're assuming our negation here, let's just, again, we're going to actually highlight it just so we can make sense of this. We're going to say let epsilon be such that for all delta greater than 0, there exists an x such that blah, 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 blah. Okay, that's this part here. So that's my epsilon fixed. The assumptions says there exists delta greater than 0 such that something or other. Now what follows on has to work for all deltas, so I can choose any delta I like, and that's all good. So I'm going to say let delta n, I'm actually going to define a number of different deltas, so I'll make it 1 over n. Then, again, my statement guarantees the existence of an x now, and that's what I'm going to do. And because we're actually going to do it for a number of different n values, we're going to choose an xn such that 0 is less than absolute value of xn minus a is less than delta, and absolute value of f of xn minus b I put the absolute value sign in the wrong place over here. Should be there. Nope, shouldn't be there either. Should be here. If f of xn minus b is greater than or equal to epsilon. Okay, so what I'm doing here is I'm choosing a sequence of delta values, remembering that my property that I'm assuming to be true is supposed to hold for any value of delta I like. So I'm just specifying a particularly useful set of deltas. And for every one of these deltas, I am choosing the corresponding x such that the following statement is true. Okay, because every time we see this there exists, it means that we can choose the x such that that's true. Likewise, that's how I chose this epsilon at the start. That's the one that exists. Okay, so I've chosen my delta n's, and I'm using this statement every time to also choose a corresponding xn. Right, so let's look at the sequence of delta n's first. First off, the sequence delta n, well, we know that the sequence 1 over n converges to 0. And then it follows here, if we look at this statement here, let's try and highlight in the right color. If we look at this statement here, if delta n is converging to 0, then the corresponding xn, that should be a delta n, the corresponding xn has got to be converging to 0 as well, or to a, sorry. Okay, because that absolute value of xn minus a is getting squeezed to 0, and hence the sequence xn converges to a. But the sequence f of xn does not converge. As the absolute value of f of xn minus b is greater than or equal to epsilon for all n. Okay, so we have built a sequence, and we use that to show that my x sequence converges, that's this part here, but my f of x part does not converge. Therefore, the limit cannot, if I assume this negation here, this f of xn does not converge, therefore the limit cannot exist. But if we go back to the start, we've assumed that the limit exists, and therefore we have found our contradiction. Limit exists implies the Epsilon-delta property. Okay, so this was a bit of a headache to do, mostly because we have complicated expressions involving lots of variables. So if we just lay it all out from the start, and I'll just run through this one more time, kind of the general strategy. Our strategy was contradiction, so we know that we had an A implies B situation. If we're doing contradiction, then we assume A and not B. That's what we did at this step here. To figure out not B, we had to calculate the negation of the Epsilon-delta property. We expressed that in symbols to make the negation easier, and realized that, okay, to negate it, we just had to flip all of the quantifiers and replace the implication with the A and not B thing again. And then we just went through kind of methodically. The first quantifier was that there exists, that was this one here, and so we chose that one automatically, just guaranteed by the there exists statement. Now we had a for all deltas, so that means we had some free choice. So we chose a particularly useful set of deltas, delta n is 1 over n. We chose n of them because we're trying to use this to build some sequences. And then, no matter what value of delta we choose, i.e. for every delta n that we came up with, the next quantifier was there exists. So every time we saw there exists, that means we can choose the thing such that whatever follows is true. Okay, and so this part here came directly from this part here. Lastly, we just had to stare at that a little bit and just see that it actually told us what we wanted. It told us that as delta n converged to 0, xn must therefore converge to A, because it gets squeezed in by this inequality statement here. But actually, f of xn, there's no way it could converge to b, because it's always going to be greater than or equal to epsilon, no matter how far you go along with the n's. And that was our absurdity, because we had assumed at the beginning that our limit definition held, which was that every sequence converging to A had its sequence of function values converging to B. And here's an example where that's not true. So overall, therefore, our original implication up here is actually correct, and we have finished proving it. All right, that was a bit of a marathon. So in our next video, we'll do some examples of how to actually use the epsilon delta definition to show some limits. But for the time being, take a break, and we'll catch you next time.